G'day viewers, I did a video about these PZEM-004T energy meter gizmos a couple of years ago, and before that on these similar energy meter displays. The essential difference between these and these is these have a display, whereas these ones stick their output on a serial port, which together with an FTDI USB to serial adapter, you can log it, what comes out of that, to a computer. Otherwise they're fairly similar. They can be powered either with, they can measure the current either with an internal shunt like this one, or via a current transformer like this one. And there's the one that comes with this guy. These things are pretty crappy, but at least you get a current transformer. I don't know if that can be used on this. I'll try that. Anyway, different ways of measuring current, different ways of outputting the data, but one thing they all have in common is the way that the electronics is powered, which is via a capacitive divider using this big capacitor and that largest resistor in there. Takes the mains voltage and drops it down to 12 using a Zener diode, and then there's a onboard regulator to produce 3.3 volts for the chip. Now that's normally not an issue, the way that they're powered, because normally you have full mains voltage available. But when you're experimenting and testing things, you might be using a variac like this here, where the voltage coming out of it will be down to 0 volts, and these things, the power supply on these, the onboard power supply, doesn't work at 0 volts. You need at least 80. Now I've got around that on this thing because mains is available before the variac, so I've jiggered the thing in there so that the power supply and the measuring point are not the same. It takes the power into the capacitive divider from before the variac, but it's still measuring what comes out of the variac and the current coming out. So that's fine on that. Things like this, current limited dummy load, no such luxury. Well, perhaps you could, but it doesn't have it. Now there's a channel on YouTube called TheHWcave, which for some reason I've got it in my head is called TheHWcave, and I can't shake it. It rolls off the tongue a little bit easier. So if I end up saying TheHWcave instead of TheHWcave, please forgive me. Now, he did a video a while ago on these PZEM-004s. To get around the problem of not being able to run at 0 volts, instead of finding an alternate source of full mains voltage to run it from, he had a very clever idea of using the 5 volts that's sitting on here when you've got the adapter plugged in, running that through a DC to DC converter to provide 12 volts into the electronics. Just as this power provided 12 volts with the Zener diode, the DC to DC converter does it instead. So as long as that's powered, the electronics is powered and can measure any voltage. Very neat. The adapter he had comes in a little plastic case, and he tried to cram all the modifications he made into that case, which I didn't like that idea so much, and I'm going to do it a different way, which I'll show you in a minute. But one other thing the TheHWcave did was reverse engineer this thing and give us schematics, and here's what he came up with. Now here's the reverse engineered schematic from the TheHWcave. There's the main chip, which is actually an 8051 core embedded with some other stuff. So it's got firmware in there which unfortunately is not available. So anyway, it's the brains. There's the regulator that provides 3 volts for that, and it gets that from 12 volts from the Zener diode, and there's the capacitive dropper from the mains. The output or the communication is via these optocouplers, which provide the isolation between mains voltage and your PC. And it's got 5 volts on it, which is needed for this LED in the receive circuit. Here is a voltage divider, so this is for powering the circuit, and this is for measuring the mains through a voltage divider, 1 meg and 750 ohms. And that resistor, as the as the TheHWcave described, that resistor is pushing it. Too much voltage can be sitting across that, so he's changed it for 2 through-hole resistors. I'm going to be using surface mount, so I'm going to put 3. On the current measuring side, the current transformer goes into this burden resistor and then some signal conditioning, and the chip can read the current. That's the original. And the modification that TheHWcave made was this, where that capacitive dropping business is eliminated and the Zener diode, the 2 resistors instead of 1 for the voltage divider for measuring the voltage, and the addition of this DC to DC converter, which runs off the 5 volts that's present there and provides 12 volts into the regulator. This is the original. Now I've redrawn it to my liking because I do that. This is the original. So again, capacitive voltage divider up there, 12 volt Zener, 3 volt regulator to the main chip, voltage divider for the measurement, 1 meg and 750 ohms, current transformer goes to the burden resistor, some signal conditioning, blah blah blah, and the serial connection is the same. With the modification, we get the DC to DC converter coming off the 5 volts, running 12 volts into the regulator. The capacitive voltage divider goes away and the Zener diode, we don't need that. I've used 3 resistors for the voltage divider for measurement, and I've added a resistor and a trim pot to hopefully adjust it to make it more accurate. Not sure how good that will work, we shall see. And likewise on the current transformer, instead of just a single burden resistor, I've made this concoction, which hopefully also will allow me to trim the current so that we get a more accurate measurement. That's the theory anyway. So here's what I'm going to do. I've made this board, looks like that. Here it is. I haven't drilled it yet, but the idea is take off that connector and that connector, the capacitor, the resistor, the Zener diode, and maybe a couple of other things, not sure, and use the existing 4 holes, 4 pads there to connect this to a little motherboard, move the terminal block over to here. This can go there, but instead of that you can also just mount this directly onto there, so that the USB plugs in straight away there. The DC to DC converter I'm using is these guys. And it'll just sit over here, there, and trim pots here and here for adjusting voltage and current measurement, mounting holes. Yeah, because I'm not trying to fit this into a little plastic box, I'm going to embed this in something else, so it doesn't really matter how big this is for my usage. So that's what I plan to do. Right, so what I'll do now is drill this up, remove a few parts off that and show you where we're at. Right, I've drilled this board and put all the parts on it. This guy I've taken a number of bits off, the big capacitor and resistor, both connectors, that one and the other one's been moved to here, plus the Zener diode and normal diode and 4 other resistors. Looking at the original diagram, it's the capacitor, the resistor, the 2 diodes, and then 1, 2, 3, 4 other resistors. 15, 16, 17 and 18. The TheHWcave only removed those ones. He left these on because he's using the existing current and voltage sensing, but I'm trying to make it adjustable, so I've moved it onto the little motherboard. I misread a note about an error on this original reverse engineering schematic. That resistor there is not 0.05 ohms, it's half an ohm, 500 milliohms, not 50 milliohms. and I misread that, so I was thinking it was 0.05, and I misread that, and my concoction business there was wrong, so it really looks like this. Two 1.1 ohms in parallel with a 3.3 ohm and a 10 ohm trimmer in series. Okay, and there's the motherboard, and this will, using the holes from the two connectors that have been removed, this will simply sit on there, just be soldered down. I won't solder it yet till I've checked the output of the DC to DC converter, but that's what it'll look like when it's done pretty much. Okay, so take that off now. I'll stick a USB cable into here and see that we get 12 volts coming out of the DC to DC converter. Right, we've brought out the old fluke, doesn't get used very often, so we'll make use of it now. On 12 volts, I've got the USB plugged in, so see there's a light on there, so we're getting power into it. And this here should be 12 volts. 12.6, good enough. Great, so we can now mount this guy. Right, there it is soldered down. 4 joints there and 4 over there, plus 2 flying leads. This one here is the 12 volts from the DC to DC converter, and this one is from the voltage measuring, voltage sensing. A couple of things that the TheHWcave mentioned about this DC to DC converter. He said that those that are rated for less than a kilovolt isolation tend to fail. Now, I've had no experience with these, so I don't know, but I'll assume he knows what he's talking about. So he went for a more expensive one, like about 15 bucks, that had 6 kilovolt isolation. So because I'm a tight ass, I went halfway. I got one of these, which was only about 3 or 4 bucks, the IVB01S512, which takes in 5 volts, puts out 12. These are 3 kilovolt isolation. I don't see anything in here about long-term reliability at any given voltage, so maybe those sort of failures are caused by surges and some mobs around the place. I should probably put some mobs on the incoming mains in whatever I put this device into. But I'm hoping that this will do with 3 kV isolation. The other thing he mentioned was that the particular one he used couldn't drive this 470 microfarad capacitor, but these ones claim that it can drive a 560 microfarad, so it should be okay. In fact, it does work, so I'm assuming this thing's alright. Maybe I should put some mobs in there, which I'll do when I put this in a box. So let's try it out. Now here's my testing arrangement. I've got rid of the fluke because I don't think it works properly on AC volts. Might have to do a repair on that guy. But so I've got the TheHWcave. I've got a PC to monitor what's happening. So I've got a variac here going into an isolation transformer just for now, just while I check out that this thing's safe. The output from the isolation transformer goes into the unit through a current transformer, through a current shunt, so I can calibrate that to this power point, which then goes to my dummy load contraption, which is a 150 watt light bulb and a 75 watt light bulb. Now, this is all a bit hard to fit on the screen. It's all very squeezy. So we've got the voltmeter there measuring what's coming into this thing, and that program there is displaying what the measurements coming out of it. And I'm going to twiddle the voltage calibration knob. So first we've got to put some volts in. We're drawing some current. Take it up to 100 volts according to the TheHWcave. I hope you can read the TheHWcave down there. I'll try and set that to 100 volts. And you can see that is reading 97.97 volts. So twiddle the calibration knob. See the voltage changing up here. It's now the voltage has gone up. The voltage, the mains voltage is quite variable. So even wound right up, I can't quite get this to match that, and that's because I was pretty optimistic with the calculations for this voltage divider. I calculated this to give plus or minus 5% adjustment, and I think that's way too tight. So I'm going to change it for plus or minus 15%, and hopefully we'll then be able to get these two to match. I've already tested the current, and similar issue there, so I've recalculated the resistors for both of these, bought the new resistors I need, and I'll put them on now, and we'll come back and try and do this calibration again. Okay, those new parts are on as per this, which I showed just a little while ago, highlighting that these resistors have been updated, and now I can get the voltage to agree pretty easily. 82.5, 82.7, you'll see there's quite a lot of adjustment range. I can spin this well below what that says, 79 versus 82, or spin it well above. Might even be too much range now. Yeah, 88 over 81, yeah, probably is more too much range. I probably should have just tried to get it to 10%, maybe even only 7.5. Anyway, it's really about 11, minus 11 to plus 18. The current one is about plus or minus 14. And now it's hard to nail down getting that to agree with this, because the mains voltage fluctuates so much. To counteract those fluctuations, I'm going to bring in the Ferguson line tamer. This guy. I've done a video on this thing. I think it was something like anywhere between 160 and 280 volts going in, and you would get 240 out. I don't know how it knew it was supposed to be 240, or even if that's what it was, but the voltage out didn't vary much at all over a huge range of input voltage. So if I put that thing ahead of the variac, everything downstream should be running at constant voltages, constant currents. So I'll put that in. Alright, now is it any more stable? I think it is. At least that first digit's not jumping around. So I'll try and get that or that to match that. Okay, I haven't got as many digits to work with, but 82.3 to 4 looks about right. Yeah, that'll do for that. I also want to check that they track well. We've got them matching pretty good at 82.3 volts, but let's try some other voltages. Let's go down a bit, say 23.5. Whoa, oh, 35.3, that's better. Had me worried for a sec. This took a while to catch up. 35.2, 35-ish, pretty good. Wind it up. 180 volts. He says 173.5. He says 173.7. Not bad. Some more. 228.6. 229. That's still good. Still better, much better than 1%. High as I can get it. 240.6. 240.9. That cracks pretty good, I think. Right, now for the current. Now I'll swap these meter leads, turn all this up first. Swap the leads to the meter for these across the current shunt. Now this thing says 30 amps, 75 millivolts. So if you put 30 amps through it, you get 75 millivolts across the shunt. That works out to 2.5 milliohms. I've actually measured it more accurately than that. It's 2.48 milliohms, so I'll be using that figure. 1.66 millivolts. Alright, got V divided by R, so that divided by 0.00248 milliohms should be 0.669 amps, which is not what that says. Twiddle this adjustment. No, my resistor calculations are still off, at least for current. You may notice the power factor is 0.97, which is not right for a resistive load like light bulbs. It should be 1.0, and it was earlier. I think that is some effect of having the Ferguson line tamer, which is a ferro-resonant transformer with, which incorporates magic. Must be having some effect, because it was 1.0 before I used that. something to watch out for. Okay, I've done quite a bit of fiddling around with the resistor values on that for the burden resistor. The original calculation was to try and make it plus or minus 15% of half an ohm, which is the original value, and I've ended up making it going from 0.6 of an ohm to 0.9 of an ohm to be able to accurately get half an amp showing. And the trouble is it's not linear. If I wind the voltage up so that the current goes up, you'll see it no longer tracks. Yeah, 0.935, 1.1. If I go back down to half an amp-ish, in fact it's only accurate at the value I set it. So yeah, this current transformer burden resistor thing has got whiskers on it, and yeah, in the back of my head I knew there was more to it than just adjusting the value of the burden resistor. A bit more nuance than that. Also, current transformers have a linear response until you saturate the core magnetically, and then it flattens out. At the low end, they also have a curve before they hit the linear part. So we might be down in here, because this thing is rated for 100 amps, so we could well be down here when we're talking about half an amp, and maybe I should have been adjusting all this stuff at much more than half an amp. So yeah, there's a lot of questions going on here. Is what I've done here mucking around, screwed it up? Should I just stick with the original 0.5 ohm resistor? For the moment, if you're going to do anything like this, I would recommend that's what you do. Go with 0.0, leave the resistor alone, forget this stuff. The voltage one's good, that works and it's linear, nothing wrong with putting that in. But current, I think probably will end up having to be something like a lookup table to account for the non-linearities in the response of this thing. Probably. Don't know. I've got some experimenting to do. I've got to go back to the original half ohm. I want to try putting 10 turns of the current being measured through the transformer, which will improve its sensitivity to take us out of that bottom end curve. Yeah, there's a lot to experiment with. This video has gone on for too long already, so I'll do that, and if I come up with anything amazing, I'll make a video. But for the moment, I'd say this is a good idea. Just forget the current bit and perhaps do some calibration and compensate for what you read out of it with a lookup table. Now, one other thing to try before we close off is just checking the isolation across this DC-DC converter, make sure it's not conducting anything. We're back to measuring AC volts, and I'm doing it between the active, it's not really active because of the floating due to the isolation transformer, but voltage difference between that and the earth terminal on the low voltage side, and wind it up to full voltage, and we're seeing 26 volts. Now, is that really dangerous or not? Well, if I just grab some resistors, 39K, first thing I saw. If I put one of those between earth and the active, that voltage drops down to 1. So if 39K can reduce that 26 volts down to 1 volt, then it's got no power behind it, it's just capacitive coupling, and it really is isolating. At least that's my theory. So this video has been going on for long enough. My next video is going to be much shorter, I promise. So in summary, this DC to DC converter idea is a very good one, I think, especially if you're going to be dealing with situations that involve less than the minimum 80 volts that the original configuration required. And I think putting it on a little motherboard like this is also a good idea. And you can incorporate the serial to USB converter on the motherboard. The voltage calibration idea I think is good, not so much the current. That needs more investigation, and if you were to do something like this, I would suggest leave that out. Otherwise, I think that was worthwhile. I hope you found that interesting, and if you did, please give it a like. That's always good to see, and I'll catch you later.